Hello student, welcome to my class. Last class we discussed what is refractive index, how ray of light deviate from its original path. That means when a ray of light traveling from denser to rarer medium, it bends towards normal. It bends away from the normal. When a ray of light traveling from rarer to denser medium, it bends towards the normal. And what is Snell's law? Sine of angle of incident divided by sine of angle of refraction, which is equal to relative refractive index of second medium with respect to first medium. By using this concept, we have to show here refraction through a glass slab or sided glass slab. Suppose there is a glass slab like this. Clear? And this is actually three-dimensional figure. We draw here two-dimensional figure. This is, suppose there is a incident ray which is traveling this direction, and this medium is rarer medium of refractive index. You can write that is mu1, and here this medium is denser medium, or you can write mu r. This medium is denser medium of refractive index mu d, or a glass you can write mu g, and this medium also rarer medium of refractive index mu r same medium. Clear? When incident ray incident on the refracting surface or interface which is separating by two medium, because this medium glass medium, this is glass slab, and this medium is rarer medium, and this is interface. Suppose this interface x, y, and there is another interface which is equal to x dash and y dash. Now first we will see refraction through the interface x, y separating by rarer medium and denser medium, that means glass medium. Now we have to draw a normal at the point of incident, and this is normal. Like this is normal n1, and you know the incident ray make with angle normal, and that angle is known as angle of incident, that is I, and this is line of action of incident ray. But when ray traveling from rarer to denser medium and separating by a surface, then the ray which deviates from its original path and bends towards the normal, like this. Clear? Or we can write here like this direction. This is refracted ray, and this angle is known as angle of refraction, that is R. Now, for second refracting surface, this refracted ray is incident ray, and when this incident ray strike on the second refracting surface x dash and y dash, now we have to draw a normal here, and this is normal, and this normal is suppose n2. Clear? And the angle made by incident ray and normal, this angle is known as angle of incident. So these normal are parallel, so that this angle and this angle equal. So we can write this angle is here R. Now, when light traveling from denser to rarer medium, this is the line of action of this refracted ray, like this. But when traveling from denser to rarer medium, it bends away from the normal. This is normal, then it away from the normal and traveling this direction, like this. This direction. Clear? And this angle is known as emergent angle, and it represented by E. What is E? E means emergent angle. Emergent angle, and this ray is known as emergent ray. Emergent ray. Clear? Okay. This is line of action of incident ray. When this incident ray suffering different refraction through this glass slab and which coming out the emergent ray, and these two rays are parallel. That means this is line of action of first ray and this is the emergent ray. This line of action of incident ray and emergent ray are parallel to each other. So refraction through glass slab, if we discuss for refracting surface x and y, for xy interface or refracting surface, we can use Snell's law. By using Snell's law at this point, suppose this point A and this point B, or fast refracting surface we can use here, that is sine of angle of incident divided by sine of angle of refraction equal to refractive index of second medium. Second medium means the refracted ray traveling which medium, that medium is known as second medium. And what is first medium? The incident ray traveling which medium. So here second medium refractive index, that is mu g, or we can write mu g, and rarer medium, that is equal to r rarer medium, or can we write that is mu g divided by mu r. We already know about this relation, and here angle of incident I and angle of refraction which is equal to r. Clear? Okay. Or if we cross multiply this relation, or you can write again this relation, that is sin I divided by sin r equal to mu g by mu r. This is equation number 1. Similarly, there is another interface x dash y dash. In interface x dash y dash interface, if we use Snell's law here, then sine of angle of incident divided by sine of angle of refraction which is equal to mu 2. And here mu 2 means this medium, this is incident ray traveling this medium, this is refracted ray for this interface. So this medium is rarer medium of refractive index r with respect to incident medium, that is g. But here angle of incident, this angle is angle of incident, r is here. So you can write here angle of incident which is equal to r. Clear? And here the angle of refracted or refracted angle here, that is E, and this relation can be write, that is g mu r divided by mu g. This is equation number 2. Now multiplying equation 1 and 2, we can write multiplying equation 1 and equation 2. Here equation number 1, that is sin I divided by sin r into equation number 2 sin I equal to here mu g by mu r equal into mu r mu g. Here cancel, then here r also cancel, the remaining part, that is sin I by sin r equal to here mu g mu r cancel, and we can write that is sin I equal to sin r, sin both side cancel, sorry, here sin e, and here this relation sin e, and this is also sin e, sin cancel, so I equal to e. That means angle of incidence equal to angle of refraction, angle of incident equal to angle of emergent. The incident ray after suffering different refraction, then the angle of incidence which is equal to angle of emergent, and this line of action of incident ray and emergent ray are parallel to each other. Clear? Now next here we have to discuss what is lateral shift. Lateral shift. Actually this distance is known as lateral shift. If you draw a perpendicular from B 2 on the line of action of incident ray, then this is perpendicular and this angle is 90 degree and which meet on the line of action at point D. This perpendicular distance small d is known as lateral shift. That means how much it lateral displace, how much the incident ray displace from its original path, and the distance is known as lateral shift or lateral displacement. And these two rays are parallel, this distance is d and again this distance also d. Now we have to find the value d or lateral shift d. That means it deviate from its, it shift from its line of action to this emergent ray, and this distance is known as lateral shift or lateral displacement. Clear? Okay. And this angle, if this angle is r, then this angle how much? Because this angle r and this total angle also we can write, suppose this angle is delta, deviation, this angle is delta, and we can write here it is r plus delta equal to I, and delta is here I minus r. Clear? So this angle we can write here, that is I minus r, this angle. Clear? Okay. We have to find this distance d. Look at the triangle. This is right angle triangle ABD. ABD right angle triangle. So we can write here, in right angle triangle ABD, in right angle triangle ABD or ADB right angle triangle, this is perpendicular because this angle is I minus r. So this is perpendicular and this is base. So we can write here sin theta, and theta is here base angle, it is I minus r equal to sin theta equal to perpendicular upon hypotenuse. This is hypotenuse, this is base. So perpendicular, which is equal to BD divided by hypotenuse, which is equal to AB divided by AB, and BD here D by, that is equal to AB. Clear? Okay. But we have to find, this is unknown quantity AB. Now we have to find the value of AB. And how can we find AB? Again there is another triangle and this angle also 90 degree. Suppose this point is M. So in this triangle AMB, again in right angle triangle AMB, this is base angle, so this is base, this is perpendicular and this is hypotenuse, but we have to find the value of hypotenuse. And suppose this total thickness of the slab, glass slab, is T, then this distance we get T, and this is base distance, so we have to use here cos theta, and theta is here r, so cos r equal to, that is base, and base here, that is base AB, sorry AM divided by hypotenuse AB, that is AB, and the value of AM, which is equal to T, so you can write here T by AB. And you can write AB equal to here AB equal to T by here cos R or T sec R. This is the value of AB. And suppose this equation is equation number 1. Now using the value of AB in equation 1, from equation 1 we can write that is sin I minus R, which is equal to D by AB, and if we replace the value of AB, that is T sec R, AB equal to T sec R. Clear? So this distance is known as lateral shift, so you can write D equal to here T sec R into sin I minus sin R. This is known as, so the lateral shift can be write d, which is equal to t sec r into sin I minus sin r equal to d. This is formula, and by using this formula we can find the lateral displacement of the ray of light which just displaced from its original path, and by using this concept, clear, and this is known as lateral shift. Suppose there is a ray which incident normally this direction, and here if it incident normally on the interface, then here angle of incident equal to 0. If angle of incident equal to 0, we already know angle of incident equal to angle of emergent, so E equal to 0. Now what is R? R also here 0 degree because normal this direction, so here R equal to 0. If you use this relation here, then D equal to T sec R equal to 0 degree, and here that is sin I minus R also 0, so 0 minus 0 equal to 0, so T sec 0 into sin 0, and the value of sin 0 which is equal to 0, and 0 into something equal to 0, so D equal to 0 means there is no lateral displacement when the ray of light which incident normally on the interface, clear. So this is the general expression to determination of lateral displacement when the ray of light incident any incident angle from this interface, clear. This is all about refraction through glass slab. Now let's test refraction through composite slab. We already discussed refraction through only glass slab. If there is composite slab, suppose there is one slab like this air medium, and there is another slab, and this is medium number 2, and there is another slab which is medium number 3, this medium number 3, and this is medium number also 1, because this medium and this medium is same medium. This medium is suppose air medium, and this medium is air medium, clear. And here refractive index mu1, this is mu2, and here for mu3, and this refractive index mu1. Suppose there is a incident ray like this air medium, and here the refractive index we can write mu1, here mu2, clear. That means this medium is denser medium and this medium is rarer medium. Why? Because the denser medium refractive index is greater as compared to rarer medium. So mu2 greater than mu1 means this is denser and this is rarer medium. When ray of light traveling from rarer to denser medium, first we have to draw a normal at the point of intersection, or at the point of incident, so this is normal. Suppose this normal is N1 and this angle is known as angle of incident I, and this is the line of action this direction, clear. Okay, we already know if we increase the angle of incident for better understanding. Suppose this is incident ray and this angle is incident angle I, and this is line of action, and we already know when ray traveling from rarer to denser medium, it bend towards normal like this, and this angle is known as angle of refraction R1, clear. Okay, and this point suppose A, and this is refracted ray. Now we already know a ray traveling in a medium in straight line path, but it changes its direction when it faces a interface. When it comes to the point of interface, then it changes its direction like this, because this is the line of action of incident ray in this direction, clear. So when refracted ray traveling A to B and reach at the interface, suppose this interface X, Y, and this interface that is X dash, and this interface that is Y dash, and this interface you can take M and this interface N. When this refracted ray reach X dash Y dash interface and strike at point B, now we have to draw a normal at incident point, and this angle also angle of incident, that is R1, clear, because this is second refracting surface, and for second refracting surface this is incident ray, and the incident ray made by angle normal is known as angle of incident, and this normal are parallel to each other, so R1 this is known also R1. Now this is the line of action, this is also the line of action of incident ray. Now when if we choose here, if mu3 greater than mu2, and which medium is denser medium? Now if we compare these two medium, then this medium is rarer medium and this medium is denser medium. So when light traveling from rarer to denser medium, it bends towards normal. So it bends towards normal like this. Clear? And this angle is known as angle of refraction. Let it be R2. Clear? This angle R1 and this angle R2. Now we have to draw a normal at the point of incident. That means this point is B and this point is C. Suppose which interface, there is a interface MN and separating by two medium. This medium is air medium and this medium is denser medium. And if you draw a normal at the point of incident, and this normal is N3, and this angle equal, so this angle is R3, and this is the line of action of this refracted ray. But here mu3 and mu1, if you compare, that is mu3 is greater than mu1. So light traveling from denser to rarer medium, and the concept of when light traveling from denser to rarer medium, it bends away from the normal, because this is normal, so it changes its direction and its path like this direction. Clear? And this total angle is known as angle of emergent, and this ray is known as emergent ray. Clear? Okay. So these are the refraction through different type of interface. First we will discuss the interface XY. For XY interface, there is separating by two medium. This medium is air medium and this medium is denser medium. Why? Because mu2 greater than mu1. If we use Snell's law this interface, so by using Snell's law this interface we can write sine of angle of incident is here I divided by sine of angle of refraction, that is sine R1 equal to mu2. 2 means here refractive index 2, mu2 of refractive index mu1, or you can write that is mu2 divided by mu1. This is equation number 1. Similarly, if we observe the interface x dash and y dash, interface, this is first interface and this is second interface, then we separating by two medium, refractive index mu2 and here refractive index mu3. But refractive index mu3 is greater as compared to mu1. So light traveling from rarer to denser medium, if we use Snell's law here, that is sine of angle of incident, which is equal to R1 divided by sine of angle of refraction, that is R2, and the refractive index mu2 with respect to mu1. So here mu3, we can write mu3 by mu2. Clear? Or you can write is relative refractive index of second medium. Here second medium is mu3 and relative refractive index of first medium mu2, or we can write here that is mu3 divided by mu2, equation number 2. Similarly, for interface Mn, if we use Snell's law here, that is sine of angle of incident, this angle is R3, so R3 divided by, this is R3 divided by sine of angle of refraction is here E, which is equal to, and refractive index of second medium, this means second medium here 1 and first medium is here 3, so you can write mu1 by mu3. Clear? This is equation number 3. Now multiplying equation 1 and 3, if you multiply equation 1, 2 and 3, we can write here sine I by sine R1 into second equation, sine R1 by sine R2 into third equation, sine R3 sin r3 by, sorry, this is not r3, actually this angle is r2 and this angle also r2, sorry, this angle also r2, so this angle is r2 and this angle also r2 divided by sin e equal to, here mu2 by mu1, mu2 by mu1 into mu2 by mu1, then mu3 by mu2, mu3 by mu2 into here mu1 by mu3. Clear? As we know, the angle of incident equal to angle of emergent, then all the term are cancel each other, so the remaining part of left hand side, that is 1 equal to, it is mu2 by mu1 and into here, that is mu3 by mu2 into or mu1 mu3. Clear? Or you can write this relation again, that is mu21 refractive index of second medium with respect to first, here refractive index third medium with respect to second, and here refractive index of first medium with respect to third. This is the general expression of this composite slab. Clear? Okay. If you take this term to left hand side, then we can write 1 by here, that is mu13, which is equal to refractive index 1 to 2 and here refractive index 2 to 3. Or if you take, we know this is reverse case or reciprocal case, if we take the above, then this will be reverse, sorry, this term will be 3 and here 1 to 3 equal to, that is 1 2 into refractive index of 3 to 2. Clear? And this equation indicate that the refractive index first to 3, which is independent of other two. So the refractive index depends on this relation, or you can imagine this relation, that is 1 by, sorry, refractive index of third medium with respect to first, which is equal to the combination of this two refractive index or to this media. Clear? That means it always depends on first and second medium. We can calculate first medium, if first medium and last medium are given, then we can calculate refractive index of the medium. Clear? So these are the refraction through composite glass slab. Now we have to find a relation between real depth and apparent depth. So what is real depth and what is apparent depth, we will discuss here. Suppose there is a surface or interface, this is one interface xy, and this interface which separating by two medium. Suppose this medium is air medium and this medium is air medium, and this medium is suppose liquid medium or any denser medium, or you can take, suppose this is water medium. Clear? And here refractive index, that is mu1, and here refractive index, that is mu2, and this is water medium. Clear? Okay. So suppose this is bottom surface of the liquid medium, and there is a point object which lies on the bottom surface, and this is object, and this distance from the interface to the object, suppose d, and the d is known as real depth or actual distance of the object from interface which separating by two medium. And we already know the ray of light which incident from the object and strike the interface perpendicularly. Here the angle of incident is 0, then angle of refraction also 0. That means it travel this direction undeviatedly like a straight line direction. Clear? It travel this direction. If you observe here, this is eyepiece actually. here, this is eyepiece, and we have to see the image of an object which is inside the water medium. So the ray of light which incident on the eye, this is eyepiece. Now second ray, actually here we have to use a paraxial ray. So what is paraxial ray? Paraxial ray means these rays are parallel to or nearly equal to principal axis, or the angle of incidence and angle of refraction is very small. We have to use this concept here. So another ray, so because we need minimum 2 rays to see an object, to observe an object, we have to use 2 rays. This is first ray and second ray. Suppose this ray which incident at this point, this straight line, this point, suppose this distance is x. Actually the distance x is very small. For paraxial ray, for convenience, we will take here a large distance x here. So now we have to draw a normal at this point which separating by 2 medium. This is normal. Suppose this angle is angle of incident and this angle also angle of incident, because these 2 lines are parallel to each other. When ray traveling from denser to rarer medium, it bends away, because this is the line of action of incident ray. It bends away from the normal like this direction, clear, and it appears to meet at this point, and we get a final image. This is final image. If we observe here, this image is final image, and this final image is real image or virtual image? This image is here virtual image. Why? Because these 2 rays are diverge to each other, and it's appear the line of action which meet on the at point I. So I is here virtual image. Virtual image. Suppose this angle is known as, this is eyepiece here. This is eyepiece and this ray. Clear? And this angle is known as angle of refraction R. So this angle will be also R. Clear? Now we have to find this distance. This distance is known as apparent depth, and this distance is taken to be d dash. So what is d dash? D dash is known as apparent depth. Actually object lies at the bottom point of the water, but it is look like in this point. So this is apparent depth and this is real depth of the object. So we have to find a relation apparent depth and real depth. Clear? Okay. Now use this triangle here. Suppose this is a right angle triangle. If we are naming here, this point is O and this point is A and this point is B. In right angle triangle OAB, in right angle triangle OAB right angle triangle, this I is here the base angle. So this is perpendicular. We can write sine F angle of incident equal to sine I, which is equal to here perpendicular upon base, and perpendicular is here AB divided by hypotenuse. This is hypotenuse OB, and AB equal to x by OB. Clear? This is equation number 1. We get the value of sin I, because we have to use here Snell's law at the interface. So next, in triangle another right angle triangle, because this angle is 90 degree. So this right angle triangle IAB, in right angle triangle IAB, sine of angle of refraction or sine R equal to, this is base angle, R equal to perpendicular upon base, and this is also perpendicular because this is base, sorry, this is base and this is base, this is perpendicular and this is hypotenuse. So perpendicular equal to AB by, sorry, great mistake by me, perpendicular upon hypotenuse H, and here perpendicular upon hypotenuse H. So AB divided by OB, here AB divided by OB, and this relation also AB divided by IB, and the value of X by this is equal to IB. This is equation number 2. Clear? Okay. If we use Snell's law at the interface XY by using Snell's law at interface XY, we can write it is sine I by sine R, which is equal to refractive index of sine I, this is sine I by sine R, which is equal to refractive index of second medium, and here 1 refractive index, and with respect to first medium, that is 2 to 1, or you can write that is mu 1 by mu 2. So this is important relation. Okay, this is equation number 1, sorry, equation number 3. Clear? Okay. So from this relation, if we use sine I and sine value here, then we can write sine I equal to x by OB into, divide here, that is IB by x, which is equal to here mu 1 by mu 2, and x cancel, the remaining part IB by OB, which is equal to mu 1 by mu 2. This is another equation IP. This is equation number 3. For paraxial ray, angle of incident I and angle of refraction R is very small. If this angle is very small, then point A and point B very close to each other. If this angle is very small like this, for convenience this angle is like this, but this angle is very small for paraxial ray, that means the point A and point B are very close to each other. So we can write AOB equal to OA. For paraxial ray we can write OB length nearly equal to for paraxial ray you can write point A and point B, or you can write the point A is, or the point B, the point B is very closer to point A. So you can write OB nearly equal to OA. Clear? This is first relation. Again, IB nearly equal to IA. That is IA. Clear? If we use this relation here, then this relation can be write, that is IB equal to IA divided by OB equal to OA equal to, that is mu 1 divided by mu 2. Clear? These are the relation between real depth and apparent depth. So here this is IA by OA equal to mu 1 by mu 2. What is IA? Here IA equal to D dash. So I can write here D dash divided by OA equal to D. That is D equal to mu 1 by mu 2. But what is D dash? d dash equal to apparent depth, d equal to real depth. So you can write here, that is apparent depth divided by real depth equal to mu1 by mu2. This is general expression. Clear? Or you can use this expression, that is apparent depth divided by real depth equal to, what is mu1? mu1 means where refracted ray travel, this second medium, refractive index of second medium divided by refractive index of first, or this is refracted, we can write here refracted ray travel. Refracted ray travel, this is incident ray travel. Incident ray travel. You have to remember this concept here. So incident ray, for incident ray, refractive index for incident ray, which is real depth, refractive index of refracted ray, which is apparent depth. This is the relation between refractive index of two different medium and real depth and apparent depth. There is another term, and the term is known as lateral shift. Normal shift. So what is a normal shift? We will discuss here. Next term, normal shift. Clear? And suppose this distance from I to O, this distance is y, and this distance is known as a lateral shift. And here the lateral shift, which is equal to this distance y, lateral shift equal to total distance minus d dash. So you can write here lateral shift y, which is equal to d minus d dash, and d minus the value of d dash. This is relation. D dash can be write here, that is d dash equal to, if we multiply this relation here, that is mu1 into d by mu2. This is d dash. So if we use this relation here, mu1d divided by mu2. Clear? This is known as y, and this is here a normal shift. Clear? Here y is known as normal shift. So normal shift y equal to d, here common, d equal to mu1 1 minus mu1 by mu2. This is known as normal shift, or you can remember this relation, that is d, which is equal to real depth into 1 minus, what is mu1? mu1 means refracted ray. This is for refractive index, for refracted ray traveling which medium, divided by mu2 means incident ray, because here ray traveling from denser medium to rarer medium. This is known as normal shift, or this normal shift is also known as the distance through which the object which appears to rest, this distance is known as normal shift. And here this distance is y, and y equal to d into 1 minus mu refracted by mu incident. So you have to remember all the concept regarding relation between real depth and apparent, and what is normal shift. Next we will start what is critical angle and total internal reflection, or short form it is TIR, means total internal reflection. Suppose there is a medium, this is important concept in optics. Suppose here there is a medium, there is two medium of different refractive index. Here the medium is rarer medium, that is mu r. Here the medium is denser medium, mu d. Clear? This is denser and this medium is rarer medium. Okay. And suppose when a ray of light traveling from denser to rarer medium, then at the point of incident which separating by two medium, now we have to draw a normal, and this normal which is perpendicular to this interface xy. Suppose this interface xy. Clear? Okay. And suppose this angle, suppose this is incident ray like this. This is incident ray, and this angle is known as angle of incident. At the time we already know when ray traveling from denser to rarer medium, it bends away from the normal. Actually this is the line of action of this ray, and it bends away from the normal this direction, and this is total refracting angle, and this is angle of deviation. This angle is known as gamma, and total angle is here R. Now if we again increase the angle of incidence I, this is I1 and I2, then the angle of deviation, the angle of refraction also again increase. This is R1 and R2. This is refracted ray when light traveling from denser to rarer medium, and again at a particular angle of incidence. This angle is a particular angle of incident. At that time, the angle of refraction which is 90 degree, this direction, and here the angle of refraction is here R equal to 90 degree. This angle of incident is known as critical angle C. This is known as critical angle. So what is critical angle? You have to remember this concept. When ray of light traveling from denser medium to rarer medium at a particular angle of incident for which the angle of refraction will be 90 degree with the normal. At that time, the angle of incident is known as critical angle. Clear? So critical angle, that angle where angle of refraction is 90 degree in rarer medium, and that angle is known as critical angle. Clear? Okay. Now suppose this critical angle C equal to 45 degree. This angle, critical angle C equal to 45 degree. Now just increase the angle, because this is incident angle. Now just increase this incident angle which is just greater than this value. That means if we again take another incident ray here like this incident ray, suppose this angle is known as angle of incident, and this incident angle which is greater than C, because C is here 45 degree. Now we have to choose a incident angle I which is equal to 45.00000000000000001 degree. Clear? Which just greater the critical angle. At that time, the interface which is separating by two medium, rarer medium and denser medium, that interface behave as a reflecting surface. And you already know the concept of reflecting surface. What is reflection law? The angle of incident which is equal to, suppose this is plane mirror, and this is angle of incident I, and this angle also angle of reflection R. Reflection here R. This is incident ray and this is reflected ray. Similarly, when angle of incident is just greater the critical angle, because here critical angle 45 degree and here incident angle 45.000000001 degree, at that time this interface behave as a reflecting surface, and this angle is known as angle of reflection. if this surface is behave as a reflecting surface like this, suppose plane mirror, then we already know angle of incident equal to angle of emergent. That means if incident angle just greater than critical angle, then the ray which is reflected back to the same medium, and that reflection is known as total internal reflection. So if this angle 45.00001 degree and this angle also 45.0000001 degree, clear? This is the concept of critical angle. So sorry, this is the concept of total internal reflection. So what is critical angle? Critical angle is a particular angle for which when ray traveling from denser to rarer medium, critical angle is a particular angle for which when ray traveling from denser to rarer medium, the angle of refraction will be 90 degree. That angle is known as critical angle. Again, what is TIR? When angle of incidence is just greater the critical angle and ray should be travel from denser to rarer medium, clear? At that time the interface or the surface or interface which separating by two medium, the surface behave as a or acting as a reflecting surface, clear? The surface is behave as a reflecting surface and the ray reflected back to the same medium. That concept is known as total internal reflection. So I repeat again my sentence, that what is total internal reflection? When ray of light traveling from denser medium to rarer medium, like this, again denser to rarer medium, if angle of incident is greater than critical angle, at that time this interface which separating by two medium, denser and rarer medium, this interface behave as a reflecting surface, and here we have to use a reflection phenomena. That means the ray reflect back to the original medium or same medium, and if this angle is I and this angle also I, this is the concept of total internal reflection. Now we have to derive a relation between critical angle and total internal reflection. This is diagram here. This is rarer medium and this is denser medium, and this is angle of incident. Suppose this angle is critical angle C. At that time the angle of refraction which is equal to 90 degree equal to R. This is angle of incident I equal to C. So if we use Snell's law, this interface or this point A, so by using Snell's law we can write sine of angle of incident, that is sine I by sine R, which is equal to refractive index of second medium. Second medium is R, rarer medium with respect to denser medium, denser to rarer. Okay, refractive index denser to rarer, or refractive index of second medium with respect to first medium. Then sine I, and here sine I which is equal to C. So you can write here, it is sine C divided by sine R. R is here 90 degree for critical angle. So you can write here 90 equal to, that is mu 2, or you can write this relation, it is mu R divided by mu D, means denser medium. So here we can use this medium, refractive index of rarer medium divided by refractive index of denser medium, and the value of sine 90 which is equal to 1. So sine C by 1 equal to refractive index of rarer medium. We all know the refractive index of rarer medium which is equal to 1. So 1 by mu of denser medium. Clear? Or we can write here sine C which is equal to 1 by refractive index of denser medium. If refractive index increase, then critical angle decrease. So this is inversely proportional to each other. Clear? So critical angle is inversely proportional to refractive index of the medium. If refractive index increase, then critical angle decrease. We know that the refractive index of glass which is equal to 1.5, and the refractive index of water which is equal to 4/3 or 1.33 or 1.3. Similarly, the refractive index of diamond which is equal to 2.43. 2.43. This is refractive index. So if you compare refractive index of diamond with other two, then refractive index of diamond is greater. So critical angle of refractive index will be smaller. So now you have to remember this critical angle for the this is glass medium, and for glass medium the critical angle which is equal to 42 degree. You have to remember this critical angle and refractive index. Next, this critical angle for water medium which is equal to 39 degree, and this critical angle for diamond which is equal to 24 degree. Why? Because here the critical angle is maximum, so it is here the refractive index is maximum, so critical angle is minimum here. Clear? Suppose if we take one example, what is critical angle and what is total internal reflection. Now application of total internal reflection. Application. So first we will discuss about application through prism. If we use prism, clear? Application through prism. Suppose there is a prism like this. This is one prism. Clear? This is front view or side view of this prism, and this angle is suppose 90 degree, and this angle is 45 degree, and this angle is also 45 degree, and this prism is made up of glass, and whose refractive index given, that is the refractive index of glass which is equal to 42 degree. So here refractive index C equal to 42 degree. Suppose there is a object here, point object, and the ray of light which coming perpendicular to this interface. When this ray of light striking the interface perpendicularly, it start refracting through this medium undeviated like this direction and strike here. Clear? Now question may arises when total internal reflection form. Total internal, the concept of total internal reflection, when a ray of light traveling from denser to rarer medium, because this medium rarer and this medium rarer, but this medium is denser medium. So when light traveling from rarer to denser, there is no total internal reflection. But when light traveling from denser to rarer medium, there are possible total internal reflection. Now this is incident ray for this interface. So we have to draw a normal here. This is normal, and this normal which is perpendicular to this interface. This is perpendicular to this interface. Now this is the line of action, this interface. we already know here the angle, critical angle is 42 degree and this angle is here 90 degree, this angle 45, then this angle must be 45 degree. But what is incident angle here? This is angle of incident because this is normal. So this angle is here 45 degree. So here the angle of incident is 45 degree. But what is critical angle condition or what is total internal condition? If angle of incident is greater than critical angle, then there is total internal reflection. That means the reflected ray come back to the same medium where incident ray traveling. So if we use this concept here, the angle of incident, that is 45 degree, which is greater than 42 degree, means critical angle. Here I is greater than C. So there is total internal reflection. That means this angle equal to this angle. So this ray which travel this direction do not pass through this rarer medium, because there is total internal reflection and this angle which is equal to this angle equal to also 42 degree. Sorry, 45 degree. Imagine that if this angle of incident is 40 degree, suppose this angle of incident I is here 40 degree and this angle of incident which is less than this critical angle, then there is no total internal reflection. At that time this ray travel in this direction or any direction towards towards rarer medium. But here this angle is greater than 90, so there is total internal reflection. Clear this concept? Now ray traveling this direction which meet perpendicularly and it pass undeviatedly in this direction. Clear? This is the application of total internal reflection for a prism. Clear? Next we can use another concept. Suppose there is a prism like this and suppose this angle is 45 degree and this angle also here 45 degree, and there is a object like this. There is a length object. First case there is a point object. So this is length object and this point A and this point is B. Now first we have to find the final ray diagram of this image. This is an object. This is object. Find its image by using this prism. And this angle is 45 and this angle is 90 degree here. And here this is made by glass, so its critical angle 42 degree. Now this point is B. The ray which starting from point B and incident perpendicularly, it start this direction straight line which undeviatedly. Clear? This is incident ray from B and this angle is here 90 degree. Now we have to draw a normal at this point. This is normal for this interface angle 90 degree here. And this angle is 90 and this angle is 45 degree and this angle must be equal to 45 degree. This is angle of incident I and this angle of incident I which is greater than critical angle 42 degree. So there is a concept of total internal reflection. Why? Because this interface separating by two medium, this is denser medium and this medium also rarer medium and this medium rarer and this medium also rarer. When light traveling from denser to rarer medium, there may possible a total internal reflection if the angle of incident is greater than critical angle. So here the angle of incident is greater than critical angle, so there form a total internal reflection, and that means this is angle of incident and this is also the angle of reflection which is equal to 45. At that time this surface behave as a reflecting surface. Again this is refracted traveling this direction, straight line direction. When it reaches this point, another interface, now we have to draw a normal at that point. This normal is suppose N2. Clear? If this normal N2, now this angle 90 and this angle 45 degree and this angle must be equal to 45 degree. So if this angle 45, then this angle also 45, which is equal to angle of incident, and this angle of incident is greater than critical angle. Now there is total internal reflection and the ray travel this direction, and this angle is here 45 degree, and this ray travel in straight line and meet at this point, and which travel undeviatedly. And if we draw a diagram here, then this point is known as point B. This point B is known as this point is B or a B dash. Again, the ray traveling from point A, similarly you can write from this A, this direction. Now you have to draw a normal here. This angle is 90, this angle 45 and this angle is 45. So traveling this direction and again travel this direction. Clear? This is the final ray and this is second ray traveling this direction, and this point is A and this point A dash. This point is A dash and this point is B dash. So this is the direction of object, but this is the direction of image. So image will get at an angle 180 degree because this is the direction of object and this is the direction of image. So by using the concept of total internal reflection, you can solve different type of problem. Clear? Or this total internal reflection we can assume for the diamond. Second application, shining of diamond. Shining of diamond. The shape of the diamond look like this. This is a diamond. If you observe this upper face, then suppose the top view of the diamond like this. Suppose there is a electric bulb which emits light in all the direction, and you already know the bulb which emit light and which radiate this direction. Suppose a ray of light traveling this direction. Clear? And strike at this point. We have to draw a normal here and its critical angle which is equal to 24 degree. This angle 24 degree. Clear? Okay. Now this is incident angle. This is normal N1 and this is incident angle, and this angle I which is greater than critical angle. That means this angle of incident which is greater than 24 degree. So there is total internal reflection like this. And again if we draw a normal here and this angle also 24 degree, total internal reflection. In this way, the ray which incident in this within the medium or within the diamond, so the diamond look like a dazzle or diamond gives shining due to this total internal reflection. Clear? These are all about critical angle and total internal reflection. Actually optical fiber not in your syllabus, so optical fiber is used on the basis or on the concept of this total internal reflection, and mirage also you can use the concept of total internal reflection. These are all about reflection through glass slab, critical angle, and what is the real depth and apparent depth, and what is the total internal reflection. Thank you.